Hello everyone, welcome back to Binomial Theorem. In this video, we are going to learn about general binomial theorem. So in Pure Math 1, you will learn about how to do binomial expansion, but in this video, we are going to generalize the idea of binomial theorem. So let's review first. How do we do binomial expansion for 1 plus x exponent n, where n is a positive integer? So first, if you still remember, we start with combination n0. And after that, the first term, which is 1, power it with n. But the second term, which is x, the power is 0. For the second term, you increase the value of the number on the combination at the bottom, which is r, becomes n1. But the power of 1, which is the first term, decreases by 1, become n minus 1. But the power of the second term, which is x, increasing by 1 from 0 to 1. And you keep doing that for the next term, which is n2, and then 1 exponent n minus 2, x squared. And then you get n3, and then 1 exponent n minus 3, x cubed. And you keep doing that until you get nn, and after that 1 exponent 0, and then x exponent n. Now, we can do simplification from here. So n0, we know that in the Pascal triangle, the coefficient always 1 for any power of n, positive integer. So n0 is 1. 1 exponent n also 1, because 1 to the power of any power becomes 1, and then x0 just 1. So that gives you 1. Plus n1, you can use the combination formula. It gives you n factorial over 1 factorial n minus 1 factorial. And then we have x over here, plus n2 gives you n factorial over 2 factorial n minus 2 factorial x squared, plus n3 gives you n factorial over 3 factorial n minus 3 factorial. And you have x cubed, and you keep doing that until you reach the last term. But nn is 1, because we know that, once again, in the Pascal triangle, the last term is 1. 1, 0 is just 1, and then you get xn. So we can simplify the factorial notation here, because we know that n factorial just n times n minus 1 factorial over n minus 1 factorial, and that will cross that out, x plus n factorial. We expand until you get n minus 2 factorial, so n times n minus 1, n minus 2 factorial over 2 factorial, n minus 2 factorial, and you cross that out. You have x squared, plus, once again, you expand n factorial until you get n minus 3 factorial. And you can later cross the n minus 3 factorial out. And you have x cubed until you reach xn. So, the binomial expansion of 1 plus x exponent n, where n is positive integer, is 1 plus nx plus n times n minus 1 over 2 factorial x squared, plus n times n minus 1 n minus 2 over 3 factorial x cubed. And then you keep doing that until you get xn. So this is the binomial expansion of 1 plus x exponent n for positive integer of n. But now, we are going to generalize the idea of binomial expansion. This formula only works for n positive integer. But what if my n is negative number, like negative integers like minus 1, minus 2, minus 3, or maybe fraction like n equals to 1 over 2, n equals to 3 over 2, or even like irrational numbers like power of pi or power square root 2. So It turns out we can generalize the idea of this formula. So this is called general binomial theorem. So general binomial theorem, as you can see, the formula of 1 plus x exponent n will be equals to 1 plus nx plus n times n minus 1 over 2 factorial x squared and so on and so on. And it's similar to our previous expansion. But the difference is this is the general idea, generalized form. The series is infinite series, means that we don't have the last term. It keeps adding until infinity. Yeah, means that never ends. And this formula works for any value of n for real numbers. You can have negative power, you can have fraction powers, you can also have irrational powers like pi or square root 2 or square root 3 or something. But we also have condition here. This formula only works for the value of x that is this one. Modulus of x has to be less than 1. And why is that? Because if you remember, as you can see, this is the infinite series. Right? This is the infinite series. And infinite series, if you still remember in the pure math 1, in a geometric series, it only works for the value of the ratio has to be, the modulus of r has to be less than 1. Same idea, in order for this series to be converged into this value, the value of x over here, the modulus of x has to be less than 1 in order for the infinite series to be converged into this value. So same idea with the geometric series. But for this syllabus, we only usually use this for the negative integers or fraction powers. So if you have positive integer, it's better to use this one. But if you want to use this one, it's okay. But usually we use formula in pure math 1 to give you complete expansion until the last term. Now, let's apply this formula to solve the first question taken from the past paper. Find the coefficient of x cubed in the binomial expansion of 3 plus x square root of 1 plus 4x. So we can rewrite the square root of 1 plus 4x become 1 plus 4x exponent 1 over 2. Now, as you can see here, my power is a fraction. So how do we expand this? You can use the general binomial theorem formula. As you can see, the value of n is the power, which is half. But it's a bit different if you look at the formula. This is 1 plus x. This is 1 plus 4x. So you just need to replace x with 4x in the formula. So that gives you 3 plus x, and then 1 plus 4x, the first one become 1, plus nx, so n is half, x, you replace x with 4x, so that gives you 4x, plus n times n minus 1, so the power is half, and then you decrease that power by half once, which is minus half, and you have two terms there, so divide by 2 factorial, and you have 4x squared, not x squared, but 4x squared. And then you have plus n, which is half, decreased by 1, minus half, decreased by 1 again, minus 3 over 2, so now you have 3 terms, divided by 3 factorial, and then 4x cubed. So if you look at the pattern here, you have nx, in this case is 4x, and then n minus 1 over 2 factorial, so you decrease by 1 once. This one you decrease by 1 2 times, so you get 3 terms, and divide by 3 factorial. So you should remember the pattern instead of just looking at the formula. That will be faster. So, and then it keeps adding, but we don't need all of the term, which is infinitely many, because we only need the coefficient of x cubed. You get coefficient of x cubed by multiplying 3 with x cubed from here, which is this one. We need this term. and you need to multiply the second term, which is x, by x squared to gives you x cubed. So we need these two terms, and we don't need all of the term, which is infinitely many. So we just need to expand that. We can simplify that. So 3 plus x times, we don't need this, but for the practice, I'm going to just write that down, becomes 1 plus 2x. And after that, we can simplify this, half times minus half over 2 factorial times 4 square x square, and can gives you, gives you minus 1 over 8, and then 16x squared. And then this one, when you multiply them, you get plus 1 over 16, 64x cubed. Now, we can simplify again. Okay, 1 plus 2x, this one gives you minus 2x squared, this one gives you plus 4x cubed. So, to get the coefficient of, this one is infinite, to get the coefficient of x cubed, that means you need to multiply 3 with 4x cubed, gives you 12x cubed, and then x with minus 2x squared gives you minus 2x cubed, so that gives you 10x cubed. So the coefficient of x cubed is 10. So the answer is 10. Okay guys, let's move on to the next question. In the next question, we are asked to expand cube root of 1 plus 6x in ascending powers of x up to and including the term in x cubed, simplifying the coefficient. So we can rewrite this as 1 plus 6x exponent 1 over 3. So let's apply the formula until you reach the term in x cubed. So we get the first term is 1. And after that, plus nx, n is 1 over 3, and you replace x with 6x, plus 1 over 3, and then you decrease by 1, minus 2 over 3, over 2 factorial, and then x squared becomes 6x squared, plus 1 over 3 times minus 2 over 3 times minus 5 over 3. You decrease that again by 1 over 3 factorial, and then you have 6x cubed. And then you just need to simplify this. So you get 1 plus 2x, and then you calculate all of this. You get minus 4x squared. And then this one gives you plus 40 over 3x cubed. So this is the answer. We just expand until you reach the term x cubed. Now, we have the second question here. State the set of value of x for which the expansion is valid. If you still remember, 1 plus x exponent n for n is a real number has condition. It only works where modulus of x less than 1. But this case, we have 6x instead of x. So just replace that with 6x. So the modulus of 6x has to be less than 1. That means you can divide both sides by 6. You get modulus of x less than 1 over 6. That is the set of value for x for which the expansion is valid. Let's move on to the third question. In the third question, we are asked to expand 9 minus 3x exponent half in ascending powers of x up to and including the term in x squared, simplifying the coefficient. As you can see here, this is 9, not 1. Remember that the formula that we have, 1 plus x exponent n, only works if the first term is 1, not 9. So we need to do a little bit modification in our expression here. 9 minus 3x exponent half, you can take out the 9, so you get 9 in the bracket. 1 minus 3x divided by 9 is x over 3, and then exponent half. So when you take out the 9 and you can distribute the power, gives you 9 exponent half, 1 minus x over 3 exponent half. And we know that 9 half is just 3. So you get this. So whenever you have the first term is not 1, you need to take out that. You can factorize that out. So to gives you 1 for the first term. So we get this, and you can expand until you reach x squared. So that gives you 3 times the expansion start from 1 plus nx. N is half. X in this case is minus x over 3. So minus x over 3 plus the power is half and then decrease by 1 minus half over 2 factorial and then minus x over 3 square. And then we stop there because we only need the term until x squared. So we get 3 times 1. This is minus 1 over 6x. Now you can simplify this term. Gives you minus 1 over 72x squared. So you get 3 minus 1 over 2x and then minus 1 over 24x squared and blah blah blah. So this is the answer. Moving on to the next question. Here we have the expansion of 2 minus x squared exponent minus 2. And we want to expand that until you reach x exponent 4. Now, this is the power for negative power, and we can once again use the formula of 1 plus x exponent n, but once again, this is not 1, so you have to take out the 2. So let's take out the 2 first. So you get 2 times 1 minus x squared over 2 exponent minus 2, and then you get 2 exponent minus 2, 1 minus x squared over 2 to the power of negative 2. And we know that 2 exponent minus minus 2 just 1 over 4. So you can just expand the rest. So we get 1 plus nx minus 2 times minus x squared over 2 plus the power is minus 2 and decrease by 1, which is minus 3 over 2 factorial and then minus x squared over 2 exponent 2. And we stop here because we already have the x exponent 4. So we can simplify, we can simplify 1 over 4 times 1. This one gives you plus x squared. Yeah. And after that, this one, when you simplify this, you will get 3 over 4 x4. And then keep adding. So you can distribute to 1 over 4. That gives you 1 over 4 plus 1 over 4 x squared plus 3 over 16 x exponent 4. So that is the answer. Okay guys, let's move on to the next question. Here we have state the set of value of x for which the expansion is valid. Now we know that for 1 plus x exponent n, the requirement is modulus of x less than 1. So if we look at the question before, we have to focus on this, the one that has been reduced to 1. We cannot use this because this is 2, right? So we have to use the one that's already reduced to 1 as the first term. So we have to use this, so we can take this out. So instead of x, we have modulus of minus x squared over 2 has to be less than 1. So we replace x with that. And we know that negative not needed in the modulus. So we can multiply both sides by 2. So you get modulus of x squared less than 2. But we know that x squared always positive, so we don't need modulus. And after that, because both sides always positive, we can square both sides. And then you get modulus of x less than square root 2. Careful guys, square root of x squared is not equals to x. Because here, x can be plus, can be minus. But we know that the output of the principal square root is positive. So square root of x squared is equals to modulus of x, where x can be plus, can be minus, but the output of square root is positive, so we have to put modulus. So the answer is modulus of x has to be less than square root 2. Move on to the last question. This last question combines the general binomial theorem idea with partial fractions. So let's see the question. Let fx equals to 7a squared over a minus 2x times 3a plus x, where a is a positive constant. So let's do partial fraction. We have linear factor in the denominator, so we can have a over small a minus 2x plus b over 3a plus x. Remember that a is a positive constant. And then we can combine them again. You get a times a 3a plus x plus b times a minus 2x over a minus 2x, 3a plus x. Now we can just compare the numerator. We have 7a squared with all of this thing. So we get 7a squared equals to, we expand, we get 3 small a plus ax plus ab minus 2bx. Now, we can once again collect the x and the constant. So we get x in the bracket a minus 2b, and then the constant we have 3 small a big A plus small a b. As you can see, 7a squared is a constant because a is a positive constant, so we can compare with this. For this one, it's 0 because we don't have x on the left side, so you get a minus 2b equals to 0, a equals to 2b. For the second one, we have 3 small a big A plus ab equals to 7a squared. Because we know that a is equals to 2b, we can substitute. You get 6b, maybe 6 small ab plus ab equals to 7a squared. So you get 7ab equals to 7a squared. And we know that a is a positive constant, so you can divide both sides by a. So you get 7 cross out, you get b equals to small a. So big A equals to 2 small a. So that means the partial fraction will be 2a over a minus 2x plus a over 3a plus x. Maybe I need this in the future, so I'll put it here instead. So the conclusion is this one. Now, move on to the second question. Obtain the expansion of fx in ascending power of x up to and including the term in x squared. So, we want to expand this. So, we can rewrite this as 2a times a minus 2x exponent minus 1 plus a times 3a plus x exponent minus 1. Now, let's apply the general binomial theorem, but as you can see, the first term is not 1, so once again, you have to take that out. So you get 2a times a minus 1, and then 1 minus 2x over a exponent minus 1, plus a times 3a minus 1, 1 plus x over 3a exponent minus 1. Now, a exponent minus 1 is just minus half, minus 1 over a. And this one becomes 1 over 3a. As you can see, you can cross out the a. So what you have is 2 times, this one you can expand, becomes 1. And then plus nx, which is minus 1 times minus 2x over a. And we need until, x squared. Okay. So, plus n, which is minus 1, and then decrease by 1, minus 2 over 2 factorial, and then minus 2x over a squared. And then we stop there because we don't need the x cubed and stuff. Plus, we have 1 over 3. And then we have the expansion 1 plus nx, which is minus 1 times x is x over 3a, plus minus 1 times minus 2 over 2 factorial, and then x over 3a squared, and so on, so on. We don't need that, the rest. Okay, so we can simplify a bit. Yeah, you can distribute to 2, you get 2, and this one plus 4x over a, and then 2 times all of those things. Yeah, this can cross out with this, so we get 2 times 4, you get 8. So plus 8x squared over a squared. Okay, plus blah blah blah, we don't need that, so maybe I can just change it into approximately. And then plus, you can expand 1 over 3, so you get 1 over 3. This one gives you minus x over 9a. This one, you calculate all of those, you get plus x over 27a squared. Now, so we can add 2 plus 1 over 3, you get 7 over 3. And then we have 4x over a plus minus 1 over 9 x over a. So 4 minus 1 over 9. And that gives you plus 35 over 9 x over a. And then we have 8x squared over a squared plus 1 over 27 x squared over a squared. So 4 plus 1 over 27. And that gives you, 217 x squared over 27a squared. So this is the final answer. Now, the last question is, state the set of value of x for which the expansion in part B is valid. So we have two expansion. The first one is this. Remember, we have to use the one that has been reduced to 1 for the first term, and this one. So we have 2, and both of this condition has to be met. So the first one, the modulus of minus 2x over a has to be less than 1. And remember, we have to use and because both of them has to be satisfied. Modulus of x over 3a has to be less than 1. Well, once again, we don't need minus here. And we know that a is a positive constant, so we can just need to multiply by a over 2 both sides. So you get x, modulus of x less than a over 2. And modulus of x multiplied by 3a, you get less than 3a. And means that we intersect. So for the first one, modulus of a less than a over 2 means that x is in between minus a over 2 till a over 2. For this one, it gives you x in between minus 3a until 3a. And you have to use a and. So when we intersect, we know that a is a positive constant and 3a, which is bigger than a over 2. So this is a over 2 minus a over 2. This is the region. But 3a and minus 3a is bigger than that, which is this one. So the intersection will be only this one, which is inside this one. So that means the final answer, only one, which is modulus of x has to be less than a over 2. So that's is general binomial theorem. I hope you like this video and see you in the next video. Thank you.